Good afternoon, everybody. Welcome to this session on nuclear medicine innovation track number 2 out of 4 tracks. My name is Thomas Bayer from the Medical University of Vienna. I'm very happy to see whoever I see in this very grand room. It seems we have an occupation rate of about 5 or less %. We're not quite sure. Normally physicists, I'm a physicist, I normally complain for the physics sessions to be either very, very early in the morning or being assigned very, very small rooms. But now we have a huge room and we can't completely fill it. So I guess my future complaints will be subject to this critical review. Anyway, I'm really happy to see whoever made his way on this lovely afternoon on Sunday to this room. I think we have a very exciting session ahead of us. The topic, for those of you who follow the innovation track, is related to instrumentation today. We have other topics on more application-oriented aspects of nuclear medicine tomorrow, and then radiomics on, I think, Tuesday. Today we have 3 very stellar speakers, and I would very much like to invite the first speaker to the podium, Professor Simon Cherry from UC Davis, who is going to share with us his vision on nuclear medicine or molecular imaging technologies with a heavy focus, I believe, on imaging technologies. And Simon, without further ado, the floor is all yours.
Well, thank you so much. And this is a very large room, isn't it? So those of you at the back, come forward and join us closer to the stage so I can see you. So what I thought I would do today is tell you about some of the more speculative projects that we and some others are involved in. And this sort of follows on from the talk I gave yesterday. And for those of you that were there, we were talking yesterday about the concept of developing total body PET scanners. So scanners that really encompass the entire solid angle around the patient, dramatically increasing sensitivity. And yesterday I showed that we'd actually finished building the first total body PET scanner and that it's now operational. But that, although it's a big step in the right direction, there's still lots more that we can and we should do. And in a snapshot here, I think there's 3 areas. So the first is the one we've already spent a lot of time tackling, which is to improve solid angle coverage, geometric coverage, and gain sensitivity that way. We can also, of course, gain effective sensitivity through improving time of flight resolution. And I will spend quite a bit of time today talking about some perhaps non-traditional approaches for doing that. And the third area where we could still do with some improvements is in the stopping power and efficiency of our detector materials. And I'll talk a little bit about some possibilities there as well. So let's start with time of flight PET. And so here we're talking about the ability to measure the difference in arrival time of the 2 annihilation photons as they interact with the detectors. And if we can accurately measure that time difference, we can constrain the location of the annihilation. And the current state of the art is somewhere around 350 picoseconds or so in existing systems. And with that, we can localize the signal to about 5 centimeters or so. But of course, theoretically, we can do a lot better than this. And there's already in the lab setting many examples, and I showed just 2 here. There are many examples of people now pushing down towards the 100 picosecond or even below that barrier, using existing materials like the lutetium-based scintillators that we're already using in our scanners, but with some wrinkles in terms of the detectors that are used to read them out, the geometries, and the doping of the scintillator to make them faster and brighter as well. So at least in the lab setting, it's already been demonstrated that we can go below 100 picoseconds timing resolution. And so if we could get that level of improvement into our systems, we'd be gaining about another 3.5-fold or so improvement in effective sensitivity over what we currently have. And so I think that's definitely a trend we're going to see in the next few years. But there's still some limitations. Scintillation is just intrinsically a fairly slow process. And another issue is that we still use really very crude methods to get the timing pickoff that we use to determine the arrival time of the annihilation photon when it interacts in the detector. Typically, we either use leading edge discrimination, which is basically just looking for when the pulse exceeds a certain threshold in the electronics, or we use constant fraction discrimination, which is a little bit more complicated and allows us to compensate for amplitude differences of the pulses. But in both these methods, the timing pickoff really only utilizes a very small part of the overall information in the pulses. So one of the questions we've been asking is whether there might be a different approach using the same detectors we currently do, where we might be able to extract better timing information. And so we've been interested, as many others have in the field, of exploring how to use deep learning, machine learning methodology, but here applied in quite a different setting. So many people, of course, are using this in the image domain to look at methods to automate lesion detection, to be incorporated into image reconstruction. But here we're using deep learning in the acquisition setting. And the idea here is that actually time-of-flight PET is a really attractive application for these methods, because the pulses that we get out of our detectors are actually very complex signals that are pretty hard to model accurately, because you've got the response of the scintillator material, and more difficult to model is the response of the actual photodetector and subsequent electronics. So although people have done maximum likelihood modeling of these pulses, the improvements generally have been fairly modest. But of course, with deep learning methods, we don't have to worry about having all that prior knowledge. The other nice thing about deep learning in this context is that this is one example where we actually can acquire very large amounts of ground truth training data. And the way that is done is, I've just simplified it here, is that we can, whoops, that was the wrong button. Let me get the right button. Let's go forwards again. So if we put a point source in between two detectors, depending on the location of that point source, we know what the time of flight difference should be for that source location. So we can acquire a bunch of pulses that correspond to that specific time of flight difference. We can then move the source to another point and acquire another set of data. And we can do this for many different locations between the two detectors. And in that way, we can build up training data sets that consist of millions of events, if we wish, quite easily. So this creates the input that we can then put into a convolutional neural network. And so on the left-hand side at the top there, you see the two typical pulses coming from a pair of detectors that, as you can see, are overlapping. And only when you zoom in on the first few nanoseconds of the rising edge of the pulse, you see that one is slightly delayed compared to the other one because of the time of flight difference. We then encode the signal intensity as a function of time with a gray level intensity. And so what you see on the right-hand side is the input to the neural network, which is a very simple image, if you like, which just corresponds to the intensity over time of these pulses. And we feed that into the neural network as our training data. And then we do that for large numbers of events for many different time of flight values and train the neural network. We can then now acquire our test data sets, which is a completely independent set of data. And we can show that we can actually quite considerably improve the timing resolution compared to conventional leading edge or constant fraction discrimination methods. So here, when we go to a convolutional neural network with 5 or 6 layers, we're going from timing resolutions that were like 230 or 240 picoseconds down to now about 180 or so. So a pretty significant improvement without changing the hardware at all. So I think this is an interesting opportunity as we start to move towards electronics in our PET system where we're digitizing the entire waveform to employ these advanced computational methods to really take advantage of their ability to extract the relevant features from these very complex waveforms and use that to improve the timing pickoff. Now, this was done with very simple photomultiplier tube-based detectors with a single crystal. We're now extending that to more modern detectors based on silicon photomultipliers and, of course, arrays of detector elements. Now, another issue, as I already alluded to, is the fact that scintillation is intrinsically a relatively slow process. So we've also been interested in looking at Cherenkov radiation. And the idea of Cherenkov radiation is that when a charged particle travels through a medium faster than light can propagate through that medium, you get the emission of visible light. It's light in the visible part of the spectrum, also in the ultraviolet part of the spectrum. And it's a little analogous to the sonic boom, the shock wave you get when you travel faster than the speed of sound, except this is a shock wave of light, if you like. And the amount of light that you produce depends on the energy of the charged particle and the refractive index of the medium that you're moving through, as shown in the equation on the right-hand side. And Cherenkov radiation has been used for a number of applications in our field. It's been used to perform optical imaging of beta-emitting radio tracers. So all the positron emitters, for example, produce, of course, positrons in tissue that transiently are traveling faster than the speed of light. And so if you do an FDG scan in a mouse, for example, you can also detect optical radiation coming from the Cherenkov effect in those animals as well. And that's been used to good effect to image high-energy beta emitters, such as yttrium-90, for example, in preclinical models. Some people have managed to do some tomographic imaging in the preclinical setting with this. And people are even looking at it as a way to activate phototherapies as well. But the application I want to discuss today is whether we can use Cherenkov radiation for fast timing in PET. So the idea is this, that as a 511 keV annihilation photon enters the scintillator and interacts, we produce fast electrons. And those electrons have the ability to generate Cherenkov light before you get the relaxation that ultimately leads to the scintillation light. So the Cherenkov photons come out very promptly within a few picoseconds of the interaction, whereas the scintillation light dribbles out over periods of many nanoseconds. So this is very appealing in the sense of getting a very fast timing trigger. But it's a little challenging because the signal levels are very low. Now, so this shows the concept here on the left-hand side. So if we look over time as a 511 photon interacts in the scintillator, what we're going to see is a very small burst of Cherenkov photons initially, and then we'll see the massively larger scintillation signal come out over time after that. And the idea is, can we trigger on that initial peak of Cherenkov photons? So if we go back to the equation for the efficiency of Cherenkov light production, you'll see that it depends on, it depends on the refractive index of the material and the energy of the charged particles. So we're going to want to choose a material. If we want to produce a lot of Cherenkov light, we need to choose a material that has a high refractive index. The material also has to be transparent to light that's in the blue and the ultraviolet part of the spectrum, so we can extract that Cherenkov light out of the material. And then we're going to need a photodetector that has high blue and ultraviolet sensitivity and low noise to pick up that signal. So if we consult our friendly table of scintillators and take a look at something that's both dense, so it will stop 511 keV photons well, and has a high refractive index, the thing that jumps out of you is an old friend to those of us that have been in the PET business for a while, bismuth germanate. So this was used in PET scanners in the late 1970s, 1980s, 1990s, before the advent of the lutetium-based scintillators, because of its very high stopping power. And for our purposes here, we're interested in it because it has a very high refractive index. Why don't we use bismuth germanate, or BGO for short, in PET scanners today? Well, primarily because it's a very slow scintillator, and we can't do time of flight with it. But now, perhaps, using Cherenkov radiation, perhaps there's an opportunity to revisit that question. So that's what we looked at. We looked at the opportunity with bismuth germanate, because of its high refractive index, to trigger off the Cherenkov radiation that's produced inside that material to do time-of-flight PET. So this plot shows, first of all, the transmittance of the bismuth germanate, because that's important. The Cherenkov light is the blue exponentially decaying curve that you see there. And so, as you can see, that light is heavily weighted towards the blue and the ultraviolet part of the spectrum, the shorter wavelengths. And fortunately, bismuth germanate transmits well down to almost 300 nanometers. So it is optically transparent across a lot of the wavelength ranges that we would be interested in. You can then go and simulate to actually compute what the number of Cherenkov photons should be from a 511 kV interaction inside of bismuth germanate. And so the plot on the right-hand side shows you for both photoelectric events in green, and then for Compton events that are either fully deposit their energy or partially deposit their energy in red and orange, what the number of Cherenkov photons are per event. And you can see the average is on the order of about 15 or so photons. So this is a very small signal. These photons come out very promptly, which is great, but there's only 15 or so of them produced, which means that we have to be extremely efficient in collecting that light and converting it into an electrical signal if we're going to detect it and trigger off it. But there is one thing that helps us a bit, and that is that unlike scintillation light, which is isotropically produced in the scintillation crystal, the Cherenkov light has some directionality to it. And that's because the initial fast electrons produced in the scintillator tend to be traveling in the same direction as the incoming annihilation photon. And so what these plots on the left show is the distribution of those electrons, the directionality of those electrons for photoelectric and Compton interactions, and you can see that they are preferentially directed in the forward direction, so towards where our photodetector would be. If we then look at the actual light produced, the Cherenkov light produced, you can see the first and the second Cherenkov photons that are produced are again heavily forward directed. So again, they're traveling in the right direction to reach our photodetector. So that's good. Now, as the electrons slow down and they change directions, we quickly lose that directionality. So it's only the very first couple of Cherenkov photons that are actually launched in the correct direction for us preferentially. So again, this speaks to the need to have very, very efficient ways to detect those. So that's the theory. So now let's see if we can actually experimentally demonstrate the possibility of time-of-flight PET with what is conventionally thought to be a very slow material BGO. So to do this, we use silicon photomultipliers that have the best UV blue sensitivity we could find, which is the NUV device that comes from FBK. So its response is shown in the red here. So you can see it's particularly sensitive between about 300 and 500 nanometers. And here's the Cherenkov light distribution, so it matches that well. And we took a relatively small crystal of BGO to start with, so just 2 by 3 by 2 millimeters, coupled it onto these SIPMs. And when we do that, we're able to get a timing resolution of about 270 picoseconds. And that's well within the range that we would like to see to be able to do time-of-flight PET. So this is a proof of concept. Obviously, this is with small crystals right now. We need to be able to do this with larger crystals and also, obviously, in larger scale detectors. But this does prove that, in principle at least, there is the opportunity to trigger off these very prompt photons to get timing out of materials that conventionally we would have thought of as being too slow for time-of-flight PET. And why is this important? Well, it's important when we also think about detector efficiency, because BGO has better stopping power than the lutetium-based scintillators we use in our PET scanners today by some distance, as you can see in the top table here. So both the photoelectric cross-section and the total cross-section are significantly higher. And as we've been discussing, the reason it's not used is primarily because the timing was really bad. But now we potentially have an opportunity to improve that. And if we could really do time-of-flight PET with BGO, then there's a few ways we could use that. We could either stick with the current thickness of detectors, which is about 20 millimeters in most PET scanners, and improve the overall efficiency from about 44% to 57%, and that's a fairly substantial improvement. We could go to even thicker detectors, potentially, because BGO is a cheaper material. So then we could get up to 78% coincidence efficiency, which is getting close to double this. Or if we're happy with our current sensitivity, we could achieve this with only 15 millimeters thickness of BGO. And if you combine that with less material and a lower cost material, we could perhaps bring the cost of our detectors down quite considerably, which would address one of the major criticisms of this total body technology we were talking about yesterday, which is with that amount of detector material, the cost is going to be high. So by going to more dense materials, that offers, and cheaper materials, it does offer us a prospect of perhaps addressing that cost issue. Now, another technology that's been looked at over the years for PET are semiconductor detectors. And the attraction there is that these are direct detectors. So scintillation detectors are indirect. The photon comes in, interacts, produces visible light. The visible light then goes ahead into a photodetector and creates electron hole pairs or electrons that form the signals. There's a two-step process. With semiconductors here, what we're doing is direct interaction. The 511 photon directly interacts in the semiconductor and produces electron hole pairs that we collect. And this leads to really excellent energy resolution. So at 511 keV, you can get better than 3% energy resolution. But the criticism from a PET perspective has been the materials available have relatively low stopping power. So cadmium telluride or cadmium zinc telluride, which is a closely related material, are quite popular and have been used at lower energies for SPECT imaging. But their cross-section is just not high enough for effective imaging at 511 keV. And also, you get very poor timing because you have to drift the electron hole pairs across the device. This is an intrinsically slow process, and so the timing resolution of these detectors has generally been very poor, several nanoseconds typically. But here's a material that has some interesting properties that might change those considerations somewhat. So thallium bromide is a semiconductor. It has a high effective atomic number, high density. So its stopping power is extremely good. As you can see on that chart there, the stopping power of thallium bromide actually exceeds that of bismuth germanate that we just discussed, and it's significantly better than the lutetium-based scintillators. So it has the stopping power we would like. We can achieve very good energy resolution, again, of a few percent using this material. But how do we overcome this issue of the timing being so bad? Well, thallium bromide has some interesting optical properties. First of all, if you look at a crystal of thallium bromide, it's actually pretty transparent. Now, most semiconductors are not transparent, they're opaque, because they have a small band gap. But thallium bromide has a large band gap, which means that visible light can pass through that material pretty well. And if you look at the transmission, or in fact, in this case, the absorbance of the material versus wavelength, you can see the cutoff is at about 460 nanometers. So light above that wavelength gets transmitted very well through the thallium bromide material. The other thing you'll see is that the index of refraction of thallium bromide is extremely high. It's 2.6. So this should be ringing bells in your mind based on what we just discussed about Cherenkov radiation, because here I have a material that's very dense, has a very high refractive index, and has good transparency. So therefore, I should be producing a fair amount of Cherenkov radiation, light, in this material when my 511 keV photons interact, and I should be able to get that light out of the material. So again, we can go ahead and run simulations to actually calculate what the amount of light produced would look like based on the transmission of the material. And so here we're predicting, again, we're going to get a small number of photons, something on the order of 11 photons or so per interaction. And so now we can set up an experiment, which is shown here, where we take a piece of thallium bromide semiconductor, and we're going to now optically read it out with a silicon photomultiplier. We're going to take the optical Cherenkov signal and use that as the timing trigger. And we have a reference, a standard scintillation detector as the reference on the other side. And with that, we were able to show that we can get about 350 picosecond timing resolution in a semiconductor. So this is about an order of magnitude better than anybody's been able to do using the charge signal, by again relying on the fact that we're producing these prompt optical photons that we can use to trigger. So the ultimate idea here is that we're going to create a hybrid detector, a hybrid semiconductor detector with an optical readout. So we will, of course, still collect the charge signal because we will use that for energy resolution, and for positioning. But now we will use the Cherenkov photons produced in the material when the 511 photon interacts to trigger a silicon photomultiplier for the timing signal. And so one implementation of that could look as is shown on this slide, where we have the electrode structure for the semiconductor readout here that will drift the charges and collect the charge signal, and a silicon photomultiplier on one of the other faces to collect the optical signal. And so perhaps with this approach, we can use charge induction for the 3D positioning and energy resolution and the Cherenkov light for time of flight. So those are some fairly pie-in-the-sky ideas and thoughts about some different ways to approach timing with PET, allowing us to use some materials that I think are very interesting, thallium bromide, and also a material that we loved in the past, bismuth germanate, which offer outstanding stopping power. So those are just some of the things that we've been working on. There's lots of other activity in the field as well, and so I wanted to finish with this slide, where I'm listing, I think, some of the things that I think we're going to see happen in the future. So first of all, I think there's definitely going to be a move towards much better geometric coverage, maybe total body imaging in some cases, but maybe just extended axial field of view in other cases. I'm hopeful that at some point we will move away from the current scintillators, which, although they're good, definitely have some drawbacks. The primary drawbacks being that they are pretty expensive because of the high cost of lutetium oxide as a raw material. And also, the lutetium is slightly radioactive, which also means that when we want to do low activity studies, we have a fairly significant background in our scanners as well. I do believe in the not too distant future, we will cross that 100 picosecond timing resolution barrier in systems. I think that will probably happen in the next 5 to 10 years or so. We're going to go to three-dimensional positioning in our detectors. Most of our detectors are currently two-dimensional, so we just get an XY position. We don't get the depth. I think that will change with time as well. And I think we'll get much more sophisticated in how we handle the data coming out of our detectors. So rather than just triggering and integrating, I think we're going to digitize the entire waveform and then use much more intelligent ways to extract out the three position coordinates, the timing information, and the energy information. And of course, this all needs to be folded in with advanced reconstruction methods that will continue to model the physics and the statistics, and perhaps increasingly also the biology. And naturally, we will continue to integrate with advanced anatomic imaging through CT or MRI. So I want to thank the people in our lab that contributed a lot of the data for the talk today, particularly Eric Berg, Sunil Kwan, Greg Mitchell, and Gerard Arino, and our collaborators at RMD on the thallium bromide project, and at FBK, who provided these very high sensitivity SIPMs for doing the Cherenkov work, and also acknowledge our funding from the NIH. Thank you.
Thank you very much, Simon, for sharing your perspective on the future of PET. Any questions? I think we can allow for 2 or 3 questions from the audience. Otto, I'm sure you're the man who doesn't need a microphone.
It's really fascinating. I have one question, and you actually talked about this at the end. I mean, when we reconstructed the data, and especially with your Explorer, the acceptance angle, we are still kind of tied to sinograms, or when you do the reconstruction. Is there a better way to do this than always actually coming back to sinograms and having a very limited, acceptance angle, because you have to spread it out and combine the coincidences?
So Otto's.
Yeah,
so Otto's question relates to whether we always need to reduce the data back to sinograms again, particularly as we go to these very extended field of view systems with very large numbers of lines of response. And certainly, in these systems, the number of lines of response start to exceed the number of events by some considerable factor. So in almost all cases, you're going to be doing list mode-based reconstructions. You're not going to be creating sinograms. Doesn't make sense anymore. I mean, a lot of people are doing list mode reconstruction anyway now, so that trend was already happening, but this just makes doing sinograms almost obsolete, except for perhaps rebinning events into sinograms just for quick, QC reasons, just to get a quick check of the data.
Follow-up question, why don't you using your Explorer all the said you only use very limited acceptance angle. If you just go this list mode, then we really can take everything we have, right?
Yeah, and so it's a question. So Otto's asking about the Explorer total body scanner and why we limit the acceptance angle in the axial direction. And there's two answers to that. So first of all, if we want to process coincidences in real time, because of the very large number of detectors in that system, and because of the diminishing returns as you go beyond a certain acceptance angle, there's just a trade-off that makes it sensible to limit that to about a plus or minus 5 segment difference, which is still about 1.30 meters or so in terms of the obliqueness of the lines of response. So, but we will have the capacity, at least for research applications, to pull all the data off the scanner and process it. And so it's only if we want to do real-time coincidence formation for more standard clinical applications that we would throw some of that data away. And we're really not throwing very much away. It's only the very most oblique lines of response where the attenuation through the subject is very high, the scatter fraction is really high, and so those lines are not really adding that much information.
Simon, it may be a naive question, but did I understand you correctly that you're advocating to use standard crystals or scintillators, but with advanced electronics and also using deep learning to basically push up the timing resolution?
I think I'm advocating that deep learning has a role on the data acquisition side as well. And I think the interesting thing there is that there are ways, and time of flight is perhaps the best example, there are ways to get ground truth data, which is such an important part of these applications, and actually measure ground truth data. And that makes, I think that's the reason it was so successful in this particular example, because you have really good training data sets and lots of it. And I think it can make a difference, yes. And it's essentially for free. So why wouldn't you would have to do quite a lot to improve your timing resolution by 40 picoseconds or so at that level. And here you get it just by an algorithmic trick, essentially.
And if I may, I have one more question. You came up with this thallium bromide, if I'm not mistaken. Mm-hmm. What surprises me is that every now and then we see talks by key people like yourself, and they pop up with a new crystal or a new scintillator.
It's not a new material. I mean, that material's been around for quite a while. There's really only two places in the world that are really focused on it. There's a group in Japan that's done some really groundbreaking work in really understanding how to make that material in high quality, and then RMD, our collaborators in the United States, have subsequently worked on it as well. So it's just a material that has not got a lot of attention, and it popped out of a search that we did, and it turns out to look pretty promising. Now the problem is, and the reason it's a long development road ahead is, we've had two groups spend a few years trying to make this material. Now you compare that with the effort and investment that's gone into cadmium telluride and cadmium zinc telluride, or silicon, and we're so far away from that still. So the ability to grow huge pieces of this at very high quality, at very low cost, we've got a number of years to go. But I think it is intriguing that we shouldn't give up on semiconductors because of timing issues. It just shows you think about it in a different way. Sometimes you can find ways to get signals you weren't expecting. And I think that was part of the motivation for presenting this here today, is that I think as a community we should try and think perhaps beyond the obvious, which we've been doing, which is lutetium-based scintillators, SIPMs. It's great, but I think there's some other opportunities out there that as an academic community we should be exploring.
Mm-hmm. Okay, thank you. Any other questions from the floor, from the few people who are in this huge room? No? Okay, well, thank you very much, Simon. And I'd like to call the third speaker to the stage. We're now moving from instrumentation to ancillary devices and now to data processing. And it's my particular pleasure to announce a native speaker, really from the local region, Sydney, Dr. Kathy Willison, working with Dale Bailey, and she will present her thoughts on the next stages in data processing with a particular focus on quantitative SPECT. Thank you very much.
Is this one on? I take it?
Yeah, forward, backward.
Okay.
Does this work?
Thanks very much. everyone, for sticking around to the end of the day to hear my presentation. And thank you very much, Thomas, for the invitation to speak, even though it was with a few daunting names. I'm going to be talking on the future of quantitative SPECT, particularly the potential of quantitative SPECT as a more mainstream clinical tool. And I'll also sort of have a look at some of the more recent literature that perhaps points us in the direction of some of the trends that we're seeing and where we might perhaps see the greatest impact of the inclusion of quantitative SPECT data. So if we consider a bit on the history and the development of quantitative SPECT, I think it really goes back to 1999. That was when the first hybrid SPECT CT system was introduced, and that was the GE Hawkeye. And as most people probably remember, this had a particularly low resolution CT associated with it, which was ideal for attenuation correction and a bit of anatomical localization. In 2004, so a few years later, both Siemens and Philips introduced a hybrid SPECT CT system with clinical CT, meaning that it was capable of producing diagnostic quality CT data. Following that, it wasn't until 2013, so nearly 15 years after the introduction of clinical SPECT CT, that we actually have a vendor-produced quantitative SPECT CT system at our disposal, and that was the Siemens Intivo SPECT CT system and their XSPECT quant algorithm. Initially, it was just for technetium, and as you can see in the image, it's capable of producing data that's in units of radioactive concentration, and so SUV were applicable. Shortly after this, GE also came out with the NMCT 670 and the Q-metric software, again capable of quantitative imaging. The main difference between the two scanners being that the GE system uses the digital detector technology of the cadmium zinc telluride detectors, and so it has a bit of an improvement in terms of energy resolution and system sensitivity. In 2016, Siemens also extended their XSPECT quant algorithm to include other radionuclides, namely indium-111, lutetium-177, and also iodine-123. So this is sort of where we're at the moment with SPECT CT. If we compare that to the path that PET CT has taken, certainly it was around the same time in 1999 that clinical prototypes of PET CT were introduced, and shortly afterwards the first commercial PET CT systems became available from the major vendors in 2001. And at this stage, PET was really intrinsically quantitative, so it was already producing data in units of radioactivity concentration, or SUVs if you please. So as you can see, the path that SPECT CT has taken to reach quantification in mainstream clinical manufacturer-supplied systems differs quite a lot to the way that PET CT developed. And I suppose there's a few reasons for that. Potentially the way that PET initially was quite research-focused versus SPECT, which was adapted into clinical practice very rapidly. Certainly having that research orientation meant that quantification was necessary. Also things like the need for attenuation correction due to the additional attenuation because we have coincidence photons travelling the entire width of the body, and also, I guess, the ease at which that can be applied based on transmission data versus with SPECT, where we have single photon being emitted from various depths within the body. So there's a number of reasons why perhaps this may have occurred this way, but nonetheless, we're now in an era where we do have, did I push the wrong button? We do have quantitative SPECT provided to us by the vendors, and I guess the question is, now that it will potentially become much more mainstream, what are we going to be doing with quantitative SPECT? How is it going to impact on our general clinical standards and protocols? It's definitely worth saying that quantitative SPECT itself is not new. It has been around for a long time at very select institutions that have that in-house expertise, the skills to write their own software and perform the corrections that are necessary for quantification in SPECT CT data. And these are a few review articles which go through some of the published data, and in particularly the accuracy of the quantitative results from that SPECT reconstruction. I'm not going to go through this in detail, but this is really just the table of results from each of those publications, pointing out the fact that there's a number of institutes that have achieved quite accurate quantitative SPECT reconstructed data. It's covered a range of different radionuclides over the last sort of 15 years. But what you can really notice and appreciate when you go through these publications is that there hasn't really been a standardised approach to how that quantification is achieved. There's variation in terms of which corrections are included at certain institutions and some are not. There's also a lot of variation in the approach to how those corrections are performed, how they're modelled and how they're implemented. But nevertheless, we can see that quantitative SPECT has been around for some time, just not at the manufacturer level. Also, the accuracy with which quantitative SPECT can be achieved is generally within 10% of true concentration values that our reconstructed data is producing these estimates. But certainly we do know that that breaks down for the smaller volumes, particularly given the inferior spatial resolution of the SPECT system over the PET system. So partial volume effects are certainly something that have been an issue for SPECT quantification and certainly still are. In terms of what is required for quantitative SPECT data, I guess very similar to what's necessary in PET as well. Attenuation correction certainly is an absolute must. Nowadays, and for several years now, the CT data has been used to perform attenuation correction for SPECT, just as it is in PET. Scatter correction, I think, is probably one of the main areas of variation across SPECT reconstruction algorithms that are achieving quantification. Typically, energy window-based methods are used, either the double or the triple energy window method, but there are also transmission-dependent scatter correction methods which have been very successfully applied, compared to PET, which does use the CT data for the scatter correction. Dead time correction historically hasn't been as big an issue for SPECT quantification as in PET because we haven't had that same really high flux of photons impacting on the detectors. However, having said that, if we're looking at certainly applying quantitative SPECT for something in the theranostic sphere or for post-treatment dosimetry, we're going to be dealing with high amounts of activity in the field of view. So certainly dead time correction is an issue and I think it does need to be addressed. Typically in SPECT it's done by application of a scalar post-reconstruction and that measure is based on previously performed experimental data. This is in comparison to PET, which is sort of a real-time, dead-time measure at the detector level. There has been advances in the approach to dead-time correction for quantitative SPECT, namely the Intivo system from Siemens certainly has a new method of using companion sources attached to the detectors to get an estimate of real-time dead time and what correction is necessary for that. Distant-dependent resolution variation and correction for that. Certainly we're all aware that as the collimator or the detector moves further away from the patient, the resolution does deteriorate. In SPECT, we've got varying radius of rotation for our projection, so this needs to be taken into account. For PET, perhaps a bit more straightforward because we have that fixed ring geometry. Decay correction and correction for branching ratios of radionuclides typically has not been implemented in SPECT CT quantification. Obviously, it's routinely applied for PET. And then, of course, system sensitivity is a measure that does need to be performed with a great amount of accuracy. Historically, it's not been implemented for SPECT, but this certainly will be changing with sort of that manufacturer-introduced approach to system standardisation. Of course, with PET, it's inherently included in the DICOM data, and it relies very heavily on the cross-calibration of the in-house dose calibrator. So that's what is certainly required. In SPECT, I think there's been some additional obstacles in achieving this. Obviously, over the years, there has been this lack of standardisation because we haven't had as much involvement from the vendors, and that certainly has changed now. I think one of the major factors and major hurdles for quantification in SPECT is the fact that a lot of these corrections and the way they're modelled will differ depending on the radionuclide that's being imaged, depending on the collimator that's being used, the crystal thickness and the energy window width, so forth. So it does sort of complicate things a little bit further and perhaps requires a bit more work to implement it, certainly in the initial stages. Also, there hasn't been much guidance on acceptance limits, quality assurance or quality control programs. And if we want to implement it in mainstream clinical use, that certainly needs to be in place. But despite all these obstacles, quantitative SPECT has certainly seen a big growth in terms of its presence in the literature. And if you just do a bit of a Google at the moment, you see a multitude of articles and abstracts, I should say, that are being released specifically looking at quantitative spec, and a lot of these are using the newly available vendor systems to achieve this, so they're not relying on that in-house expertise. And it's great to see it becoming more widely available. Also, if you have a look at these articles, it gives you a bit of an idea about what trends we're seeing in quantification of specs in terms of clinical use. Perhaps, potentially what role is it going to play? So this is a table that's taken from a review article that I did with a colleague of mine, Dale Bailey, back in 2013, and we were sort of just brainstorming on potential clinical uses for quantitative spec. So I thought I'd just go through each of these to get a feel for how they might be adopted in our standard clinical protocols. Certainly, quantification for treatment planning and treatment assessment, I think, is very much something that we'll see quantitative spec play a big role in, and we already are to some extent. The idea of theranostics, which of course has been the big buzz for a few years now, I feel that that's probably driven quantitative spec and the industry's focus on it quite a bit. This is an example of quantitative spec used for lutate renal dosimetry, generating time activity curves and dose estimates, and certainly there's a lot of examples of this appearing in the literature. Myocardial perfusion imaging, quantitative spec, obviously very desirable there. The GE system lends itself very readily to that with the additional sensitivity and speed of acquisition, if you like, on the semiconductor detectors. The idea of fully quantitative technecium lung scanning for ventilation perfusion, this is something that we've been interested in for a long time at the clinic at Royal North Shore Hospital. We've done a fair bit of work on quantifying the lobar function for both ventilation and perfusion and using this to estimate loss in lung function for patients that are having surgery to remove lung cancer. The role of quantitative spec in technetium MAA for planning of radioembolization, this is in the literature a huge amount. And I believe will continue to grow, particularly based on the recently implemented European mandate for compulsory dosimetry on all patients receiving radiation therapy, including radionuclide therapy. In this case, we're relying on the fact that that MAA is a good representation of where the therapeutic radioembolization particles will go, which is of course a bit of an unknown, but certainly to have some information on what you think lesion doses will be, what you think healthy liver in this case will be receiving at the time of treatment, I think is very comforting for the clinicians who are prescribing the activity at the time of the treatment, and I know that we use this very heavily at our facility. Looking at the literature, I think the standout for what's been appearing, particularly since the introduction of both the Siemens and the GE system, is technetium bone scanning, doing whole body spec CT with quantification to get SUV measures in bone. There's a number of articles now demonstrating a significant difference in SUV of bone metastases versus degenerative disease, for example. And I feel that this is something that could very easily be adopted into mainstream clinical practice. Iodine 123 quantitative spec for brain studies. This is actually really building on the back of the work that's come out of Japan that's been done for about the last 15 years. They've had an incredible success with in-house quantitative spec being used across all of the country, over 100 centres, more than about 30,000 patients that have been part of their iodine 123 quantitative spec investigations. So I certainly think we'll be seeing a lot of interest in that as well. Thyroid imaging, whether it be for sort of SUV analysis pre and post treatment, determining individual dosing levels for iodine 131 and so forth. Again, I think that's something that would lend itself very readily to spec quantification. Myocardial perfusion imaging, quantitative spec, perhaps looking at some sort of dynamic imaging. Other areas, in particular things like gallium-67 citrate infection imaging, looking at how disease is responding to therapy, certainly the use of quantification, SUVs, or even just concentration measures in areas of disease, I'm sure would be very useful in this setting. And then finally, measuring radionuclide biodistribution and dosimetry. This is something that I think we'll be seeing a lot of, and quantitative SPECT clearly has a lot to offer here. Traditionally, a lot of this work's been built on sort of 2D planar data, which has issues in the quantification stage and also has issues in the organ delineation stage. So if we can address both of those things with 3D fully quantitative SPECT CT, I think that's a very big step forward. And there is a huge amount of literature on this now. Some of the advances in technology that will also sort of coincide with this development and adoption of quantitative SPECT CT, for example, the use of whole body SPECT CT. This has certainly been used a fair bit over the last few years. And up here I have an example of some data provided by our PhD student, Hyunju Ru. She's been working on reprojecting 3D quantitative SPECT data into the same projection angles for comparison to conventional bone scans. The idea being that, you know, if clinicians are going to be moving to reporting from 2D data into 3D data, we'd like to make it as easy as possible. So if we're able to reproject the data that they'd be used to looking at, that could certainly ease that transition. Dose reduction techniques are, of course, always at the forefront of our mind and of the technological advances. In CT, we've seen that automatic exposure control make a big difference. Iterative reconstruction, where available, also significantly reduces the dose from CT. For SPECT, there are the development of new materials, such as the digital detectors. They do have a greater sensitivity, so perhaps that can be used to give lower doses to patients. Also, a lot of research in things such as the Compton camera, modelling scattered photons so that we improve the sensitivity of our systems there. Analysis software, there's more and more that you're hearing about things like automated segmentation and machine learning. That can certainly play a role and I think really, make things more streamlined in the clinic. And then, of course, hardware advances as well. Again, this idea of new detectors that can speed up things, particularly if we're looking at replacing a 2D whole body image with, for example, a 3D whole body SPECT CT. We need to be keeping up with the acquisition times that we're used to reduce the clinical burden. In terms of advances that are happening in the clinic and why perhaps we will see a push towards SPECT quantification, I think it's fair to say that emerging therapies and theranostics is a big one. We know that single photon emitting labels are more suitable given their half-lives matching the kinetics of the pharmaceutical biodistribution for certain studies on, for example, peptides and antibodies. Also, obviously, the therapeutic agents we're dealing with are beta emitters and usually accompanied by gamma emission. So quantitative SPECT for post-treatment dosimetry is very important. And also, now that we have some vendor support behind this and some manufacturer standardisation, I think that things are at a stage where they will be more readily adopted. There's been a few examples over the last few years of MERD pamphlets that have been published, which is really great, giving some guidance on the use of quantitative SPECT specifically for dosimetry modelling, whether it be iodine 131 or more recently lutetium 177. So again, it's really important for us to have that before we start utilising these tools in the clinic. In terms of the future of clinical quantitative SPECT, I think we will see a migration for some studies of planar 2D imaging over to 3D quantitative SPECT, for example, in the bone imaging, perhaps infection imaging. We might see the clinicians reporting SUVs as a standard, for example. I think the expectations we have will start aligning much more than the expectations we currently have for PET. We'll have mandatory SPECT quality control, maintaining that agreement between the scanner measures and the dose calibrator measures. Also things, as I said, routine reporting of SUVs, routine reporting of dose to certain lesions or certain organs at risk following therapy, and also dosimetry planning, particularly in the theranostic phases. I think this will certainly have an impact on clinicians and scientists alike. The physicists in the department certainly need to be up to date with the quantitative algorithm, what's contributing to the data, what do they need to keep an eye on, what are the acceptable limits and so forth. And as I alluded to before, the idea of clinicians adapting to reporting of 3D SPECT data versus 2D data, and getting used to having some of these other tools available, such as SUVs. Certainly the use of vendor-supplied and supported both hardware and software should make clinical quantitative SPECT easier, I guess, and certainly more widely available. And finally, I think there'll be a big impact on the radionuclide therapies and our potential to change patient management, whether this be monitoring cumulative dose in the kidneys, for example, for lutate patients, calculating the treatment activity based on predictive dosimetry from MAA, for example, things like that. I think we'll see a lot more exploration into those areas. So thank you for your time. And okay.
Thanks very much, Kathy, for what almost seemed like a roller coaster ride through quantitative SPECT.
So we're running late.
We have time for some questions. I'm curious why, and I'm sorry for being so abrasive, but why did it take so long for the SPECT community to embrace the concept of quantification?
I think it was embraced. It's just that because it wasn't widely available, there wasn't this same clinical utility that was recognised for it. I think it was sort of a bit of a vicious circle because it wasn't available, no one really explored to any great length what they wanted for, and so it sort of got a bit forgotten. Certainly, you know, when you look at the literature, there are a lot of published research studies in particular that have used it to good use, to good extent, have developed it and, you know, really validated the accuracy of it. So it was there, but because it wasn't widely available, I think that a lot of people sort of just plodded on and thought that, well, if you want something quantitative, you use a PET tracer. You know, if you don't, then just stick to SPECT. But certainly, I think that is changing a lot too, that dogma.
And I mean, you know, I'm a PET guy, but I'm curious about SPECT. So from what you demonstrated, the abilities we have to do quantitative SPECT, does it already have made a clinical impact?
I think it's maybe too early to tell. Certainly at our centre, I think
you're very hard working on this one, I know.
Yes, it is a work in progress. I guess it depends what scenario you're thinking of. Dosimetry, for example, the quantification of the SPECT is really essential to that. As you're aware, there is a big push now for dosimetry on all our patients and all the patients that are having treatment, I should say. So I think that will be one of the big drivers behind it, whether it be dosimetry on post-treatment imaging or also treatment planning from our sort of theranostic pairing agents if it's not a PET agent. I think that might be the first area we see where it really makes a big impact.
On the note of dosimetry, I should invite the audience to come to the NM Innovation Session tomorrow, because we will have a debate on the use of personalized dosimetry, and I'm quite intrigued by the fact that there are two groups of physicians who actually argue and counter-argue about the value of doing a true quantitative personalized dosimetry. But I agree with you that this could be one of the areas of application. Now, one last question I would have is you always flip-flop between quantitative and fully quantitative SPECT.
Sorry, that was just
Tell us the difference, because coming from PET, fully quantitative now seems to be a narrative for parametric imaging, and I don't think that this is what SPECT's going for.
More in the sense of intrinsically quantitative, not relatively quantitative, okay. I suppose, yeah.
All right.
So, you know, we don't require a little flask in the corner that gives us our sensitivity factor or anything like that. You know, the images are reconstructed in the correct units of concentration. Cool.
Any other questions? Does contrast agents and CT make any impact? Do they have an impact on quantification and SPECT?
It's a good question. I don't think we've seen that. I know there's people who have mentioned the effects of, for example, the Intivo system uses the CT for zoning, and that's meant to sort of improve the resolution in the reconstruction. I know there's image artifacts from that have been recognised, but I haven't really heard much, certainly not at our clinic, for the contrast effects, no.
All right, thank you very much. So if there are no more questions, thank you very much, Kathy. This closes the session. Feel free to come tomorrow to the NM session number 3 at 4:15. Thank you very much for populating this huge auditorium, sorry.